Welcome to the world of steel design, where buildings meet brains and bridges meet brawn. You see those towering skyscrapers? They're not just concrete. Underneath it all, steel holds everything together. So let's break it down. First up, what exactly is steel design? It's the process of figuring out what size and shape your steel members, things like beams and columns, need to be to support your structure safely and efficiently. Think of it as picking the perfect Lego piece for your building block masterpiece. Now, every structure faces loads or forces. Imagine you're building a house. You've got dead loads, like the weight of the building itself, live loads, like people moving around, and then there's wind, rain, earthquakes, and maybe a little dancing at your housewarming party. But hey, you can't just do whatever you want. Building codes set the rules. They tell us what's safe so no one skyscraper goes toppling over. But to really get into the nitty-gritty, we use design specifications like the AISC or our local National Structural Code of the Philippines. There are like cheat codes for making sure your building doesn't fall like a lawn chair. So what makes steel so special? It's strong, flexible, and cheap. It can bend, stretch, and still stay intact, kinda like that one friend who's always up for anything. This is what we call ductility, and it's why steel doesn't just crack under pressure. There's more to steel than meets the eye. You've got mild steel, which is super ductile, and high strength steel, which can handle more load but is a bit stiffer. We even measure this in something called the 0.2% offset method. Fancy, right? Now let's talk shapes. Steel comes in all sorts of cross sections. You've got your W shape for heavy lifting, your L shape for corner support, and C shapes that are, well, kinda like the backbone of smaller structures. Each shape has its own superpower. Steel isn't just slapped together either. It's carefully hot rolled or cold formed into these shapes, depending on what the job calls for. Think of it like baking the perfect pie crust. Precision is everything. Finally, let's talk about how we design with steel. There are two main approaches, which is allowable strength design and load and resistance factor design. ASD is like setting limits. You keep everything in a safe zone. LRFD, it's more advanced. It factors in loads and gives us a better safety cushion. Think of it like choosing between safe mode and expert mode in a video game. So whether it's that massive bridge you cross every day or the skyscraper facing the skyline, steel design is behind it all, making sure it stands strong and lasts long.
Moving forward, steel design involves selecting the appropriate cross-section of a structural member to safely and economically resist applied loads. The goal is to often minimize the weight, which translates to using the least amount of steel without compromising strength. For this, we need to consider both the shape and size of the cross-sectional area. Before we head on here is a steel design trivia. Did you know that there are different methods to design steel structures? The allowable stress design, or ASD, focuses on preventing material stress from exceeding permissible values within its elastic range, while plastic design considers failure at loads higher than the working load, allowing parts of the structure to enter the plastic range. This means that plastic designed members can handle more load but are still safe under normal working conditions. In allowable stress design, or ASD, the focus is on ensuring that the forces applied to a structural member do not surpass the material's allowable strength, keeping it safe under typical loads. By maintaining the stresses within the elastic range, the material can deform and recover without permanent damage. The key design rule is that the highest stress experienced by the member must always be less than or equal to the set allowable stress, ensuring safety and durability. Plastic design emphasizes a structure's behavior at the point of failure, rather than just its performance under regular service loads. It ensures that the structure can handle loads significantly higher than what it would typically face, providing a margin of safety before failure occurs. While failure in plastic design might mean collapse or severe deformation, the structure remains secure and functional under normal working conditions, as the design ensures safety up to those extreme load limits. Load and resistance factor design, or LRFD, like plastic design, focuses on the structure's strength but incorporates safety factors to address uncertainties in material properties and loading conditions. It applies load factors to the expected service loads, increasing them to the account for potential variances, and then uses resistance factors to reduce the theoretical strength of the member. The main design requirement is that the adjusted or factored loads must not exceed the factored strength, ensuring the structure remains safe even under extreme conditions. Now let's talk about the idea between ASD and LRFD. The main difference between allowable stress design and load and resistance factor design lies in their handling of safety and uncertainties in loads and material strengths. ASD uses a single factor of safety to ensure that working loads do not exceed an allowable limit, while LRFD uses separate factors for both loads and material resistance to account for uncertainties. This approach is more precise and efficient, providing more precision by tailoring load factors to different types of loads and using resistance factors for material strengths. LRFD also optimizes material use while maintaining safety, leading to more economical designs. In summary, ASD applies a single factor of safety uniformly, while LRFD uses multiple factors for loads and materials, providing a refined and efficient design process. In summary, steel design involves selecting the right cross-section and method based on the loads and conditions the structure will face. By using methods like ASD, plastic design, and LRFD, we can ensure that our steel structures are both safe and economical.
Today, we're diving into an essential topic in structural engineering, which is steel beam design. We'll cover the basic concepts of beams, their behavior under loads, and how to calculate critical properties. By the end, you'll have a solid grasp on how steel beams are analyzed and designed. Let's get started. A beam is a structural member that primarily supports loads across its length, causing it to bend or flex. Unlike columns that handle loads along their length, beams are mostly subjected to bending forces. If a beam also supports an actual load, meaning it's compressed along its length, we call it a beam column. Beams come in various cross-sectional shapes. The most commonly used ones are W, S, and M shapes. These are all forms of I-beams, but sometimes engineers also use channel shapes or create custom-built beams by welding plates together. The key takeaway: different beam shapes are used depending on the structural needs. Flexure design has two methods. When we talk about beam design, understanding bending stress and the plastic moment. Beams undergo various stages of stress when loads are applied. Initially, they are in the elastic stage. This is where they return to their original shape after the load is removed. As the load increases, yielding begins, meaning the beam starts to deform permanently. Eventually, the entire cross-section yields, forming what we call as plastic hinge. Now at this point, any additional load could cause the beam to collapse. The key takeaway from this is beams have an elastic and a plastic stage. Once the plastic stage is reached, further loading can lead to collapse. Now we are going to talk about plastic moment capacity. The plastic moment capacity is the point at which the beam forms that plastic hinge. It's the maximum moment the beam can carry before collapsing. Engineers use this value to ensure beams are strong enough to handle the loads they're designed for. The key takeaway from this is plastic moment capacity tells us when a beam is close to failing.
Here are the ways on how to solve the plastic moment capacity. When solving for the plastic moment capacity, Always ensure material properties are properly defined. Cross-sectional geometry plays a crucial role in determining plastic section modulus, which influences the plastic moment capacity. And lastly, use safety factors to account for uncertainties in design, ensuring the calculated plastic moment capacity exceeds expected loads.
Hello, my name is Marron Carlos, and I encourage you to reflect on the lessons discussed as they provide valuable insights. Let's explore an example that will further clarify this topic. For this example, we have to compute the yield moment capacity, plastic moment capacity, the shape factor of the given section with Fy equals 248 MPa. To compute this problem, we have to know the solution, which is yield moment capacity is My equals Fy multiplied by S. The plastic moment capacity is Mp equals Fy multiplied by Z. And the shape factor is Sf equals Z over S. For this, we have an unsymmetrical beam, and we have to solve the elastic neutral axis. And our reference will be the bottom part of the beam. For this, we have to solve the y-bar, which is y-bar equals to 50 multiplied by 160 multiplied by 80 plus 200 multiplied by 40 multiplied by 180 over 50 multiplied by 160 plus 200 multiplied by 40. And the answer will be 130 mm. Then, our elastic neutral axis is 130 mm. Then we will solve the I bar x, which is I bar x equals to summation multiplied by Ix plus AD squared. I bar x is equals to 50 multiplied by 60 cubed over 12 plus 50 multiplied by 160 multiplied by 130 minus 80 squared. Then we will add it to 200 multiplied by 40 cubed over 12 plus 200 multiplied by 40 multiplied by 130 minus 180 squared. Then the I bar x is equals to 58.13 times 10 raised to 6 millimeter to the fourth. Then we will find the plastic neutral axis. Let's assume that the plastic neutral axis is located at 40 mm from top. To check it, we will solve the area 1 and area 2. Area 1 is equals to 50 multiplied by 160 equals 8,000. Area 2 is equals to 200 multiplied by 40 equals 8,000. Meaning to say that the plastic neutral axis is located at the boundary of the two areas. Then we will solve the S, which is S equals to I over C. We have 2C in this given, but we will adopt the largest one, which is 130 mm. Then the given will be 58.13 times 10 raised to 6 millimeter to the fourth over 130. Then the answer will be 447.18 times 10 raised to 3 millimeter cube. Then we will solve the Z. Z is equals to 200 multiplied by 40 multiplied by 20 plus 50 multiplied by 160 multiplied by 180. Then the answer will be 800 times 10 raised to 3 millimeter cube. From that, we can solve now the yield moment capacity, which is My is equals to Fy multiplied by S. And the given will be 248 multiplied by 447.18 times 10 cube. And the answer will be 110.9 kilonewton meter. After that, we will solve the plastic moment capacity, which is Mp equals to Fy multiplied by Z. And the given will be 248 multiplied by 800 times 10 cube. Then the answer will be 198.4 kilonewton meter. And lastly, we will solve the shape factor, which is Sf is equals to Z over S. And the given will be 860 times 10 cube over 447.18 times 10 cubed. And the answer will be 1.79.